Welcome to The Explainer. I am absolutely thrilled to jump into today's topic because it completely shatters the illusion that upgrading to a new frontier AI model is as simple as just swapping out an API key. We're going to deconstruct a fascinating case study from an AI company called Ploy. They recently migrated their production website building agent away from its reigning champion, Claude Opus 4.8, over to OpenAI's brand new flagship tier GPT-5.6 Sol. For 4 straight months, nothing could beat Claude Opus in Ploy's evaluations. Then, GPT-5.6 Sol came along. But as you'll see, getting it to actually work required completely rewiring the architectural layers of their system. Okay, let's dive into this because you really have to see these hard numbers to understand why all this migration headache was worth it. We're talking about GPT 5.6 saw completing entire website builds in just 3 minutes and 42 seconds. That is 2.2 times faster than Claude Opus. And look at the output tokens. GPT 5.6 used roughly half the output tokens of Claude, coming in at 17.1K versus 33K. Plus, the total cost per suite dropped from $3.06 to $2.22. But hitting these numbers in production? Yeah, it wasn't magic. It required solving a whole series of hidden infrastructure bottlenecks. Here's our agenda for today. The GPT 5.6 upgrade, fixing the eval harness, taming tool arguments, solving the caching crisis, mastering reasoning replay, and finally, a developer checklist. This is our roadmap for a complete mystery-to-mastery breakdown of how Ploy actually pulled this off. All right, Section 1, the GPT 5.6 upgrade. Because upgrading a frontier model is way more complex than you might think. As anyone who builds real-world AI agents knows, provider-specific behaviors totally dictate how your stack performs. Ploy achieved an amazing 27% lower per suite cost with GPT 5.6 Sol. And that is a huge feat considering Sol's really high baseline pricing. We're talking $5 per million input tokens and a hefty $30 per million output tokens. So how did they save 27% overall? It all comes down to how the model actually writes code. To understand those cost savings, check out this comparison. On a match test, Claude Opus spat out a massive globals.css file, almost 18,000 characters long, just bloated with 174 CSS variables, most of which were totally unused. GPT 5.6 Sol, on the other hand, it produced a hyper-lean 2,500 character file using just 45 variables for a comparable page. It writes significantly leaner code. That lack of bloat drives down token costs and network transfer, which completely explains that dramatic drop in output volume we saw earlier. Moving right along to Section 2, fixing the eval harness. Getting to those cost savings wasn't an immediate win. You absolutely have to fix your evaluation harness before trusting a single benchmark number. During Ploy's first run, GPT 5.6 was actually failing tests it was solving correctly. Why? Well, Ploy's eval budgets were implicitly sized for Claude's highly sequential tool calling style. GPT 5.6, though, makes rapid parallel tool calls and frequently utilizes batched file reads. Basically, Ploy's system was penalizing the new model for working faster and in parallel. Another huge friction point was implicit thresholds. A dataset that missed a min score simply inherited a default of 1.0, which ended up harshly punishing perfectly acceptable variations. The big takeaway here? Without manually triaging your traces, an eval is just going to reward a new model for behaving exactly like the old one, completely masking its true capabilities. Let's jump into Section 3, Taming Tool Arguments. Now, what's really interesting about this slide is how GPT 5.6 alters the tool calling dynamic under the hood. Ploy's code tool has 25 parameters, but only 1 is actually required. Claude behaves super cleanly here. It sends the 2 to 3 required parameters and omits the rest. GPT 5.6, however, is incredibly verbose. It sends all 25 parameters. To fill the optional ones, it literally invents plausible unused values, like sending an offset of 0. This completely confused Ploy's file retools. And the fallout from that verbosity was wild, because the tools can distinguish intended values from those invented ones. Up to 64% of GPT 5.6's file reads returned completely empty. But since the tool returned a success message, the model had no idea it was reading blank files. It just kept trying, hallucinating, and compensating with more calls. To fix this, Ploy engineered a brilliant schema transform. First, they rewrote optional properties as required but nullable. Second, they passed this through a universal router, the Versal AI SDK. And third, they stripped the nulls before validation at the tool boundary. The result? Empty file reads dropped instantly to 0%, and overall tool calls were reduced by 30%. Which brings us to Section 4, Solving the Caching Crisis. This was the most critical gotcha of the entire migration. Initially, the cost gap made GPT-5.6 look way more expensive, but that was a total illusion. Anthropic offers organization-scoped caching with implicit partial prefix matching, but OpenAI's caching uses partitioned keys and completely drops partial prefix matching. Identical initial prompts on GPT-5.6 were missing the cache entirely, so Ploy was paying full price for massive prefixes every single time, plus a 1.25x uncached write surcharge. Ouch! Let's move to and see how this builds. To bypass this, Ploy strategically partitioned their cache keys. They couldn't use a single global key because of a 15 requests per minute node limit that spills over to cold caches. Instead, they scoped the prompt cache key strictly per workspace. Then, they split that massive 29K token static system prompt into breakpointed layers to avoid server spillover. And look at the data here. Before the fix, first call cache hits were sitting at a dismal 0%. After implementing those workspace keys, the system stabilized and the hit rate skyrocketed to an incredible 83.7%. Fixing that cache dropped total uncached input tokens by an impressive 28%. This proved definitively that the initial high costs were just a cache misconfiguration, not the model's actual price tag. Up next, Section 5, Mastering Reasoning Replay. So the crucial point is making sure the model can accurately follow its own multi-turn logic. By default, reasoning replays are transient server-side item pointers, which kept causing loop breaks in Ploy's production environment. The fix? Setting store false in the request. This forces the model to return encrypted reasoning globs instead. You absolutely must make reasoning traces self-contained so the agent doesn't break its own tool execution chains. And finally, Section 6, Developer Checklist. And this brilliantly illustrates the strict developer checklist you need for upgrading to any frontier model. Align your prompt cache keys to the model's output variants, update your tool argument parsing schemas, ensure your abstraction layers don't mask provider formats, make reasoning replay strictly self-contained, and always benchmark exclusively with production-grade evals. I want to leave you with this final provocative thought. Is your AI agent's infrastructure secretly masking a provider-specific bottleneck right now? I highly urge you to audit your own LLM stacks based on what Ploy discovered. Thank you so much for joining me on this explainer, and I hope this helps you push your production agents to the absolute limit.